Hello, everyone. This is Spencer from Hydromantis, and I'm glad that you can join us today for our monthly GPSX webinar. I have with us today my colleagues Nick Piccolo and Rajiv Goel. And Nick will be presenting today about modeling chlorination and dechlorination processes in GPSX. These are two features that recently got sort of updated and developed as part of the new version of GPSX, version 8.1, which was released recently. And so we thought it would be a good idea to focus today on some of the new and updated features in our package. So while we're doing our webinar, just as we usually do, you have the opportunity to ask questions. So if you open up the questions panel of your GoToWebinar dashboard, you will be able to type questions in there. As per usual, we will collect up the questions while the presentation is going on, and then at the end of the webinar, we'll stick around for a few minutes and answer as many of those as we can. Okay, I will hand the floor over to Nick, and you can go ahead. Thanks.
All right, thank you, Spencer. So yeah, as Spencer said, today we're going to be talking about modeling chlorination and dechlorination processes with GPSX. So I'm just going to start just going over the agenda of the presentation. I'm going to give a brief introduction to chlorination and what we do in GPSX and basically why chlorination is important. Then I'm going to talk about our modeling objectives. So basically just some key disinfection and chlorination processes that we wanted to capture in the model and the key outputs that we wanted the model to produce. And then I'm going to get into more just describing the model. So I'm just going to go into the details and explain our model more and how it achieves our modeling objectives. After that, I'll give a brief demonstration of the model in GPSX, and then we'll do, as Spencer said, our question and answer period at the end. Okay, so just for a bit of an introduction, this is a GPSX layout shown here of the conventional activated sludge process with a chemical disinfection unit or object highlighted there in red. So basically today's webinar is going to focus on what goes on inside that object. That is the disinfection model that we actually have in GPSX. And a lot of the things that I talk about today are actually new in our new version of GPSX, GPSX 8.1. Such as the dechlorination reactions and the nitrate addition to the breakpoint chlorination reactions. So basically, we wanted to do this and we wanted to update our model because chlorination is still quite important in the wastewater industry. It's still pretty widely used. And as of a 2008 WERF report, we saw that about 72% of wastewater treatment facilities that disinfect use chlorine disinfection. So we feel that it's very important to be able to model it well. Just a bit of a background now on chlorination and dechlorination just in general. Basically, some advantages of chlorination is that chlorine is a strong oxidant and it can disinfect very rapidly. It inactivates bacteria and viruses and it can control pathogens. And compared to other disinfection options, it can be quite low cost, but still very effective. But a major disadvantage is basically that it reacts with dissolved organic matter to create disinfection byproducts, also known as DBPs. And these can have ecological and health effects that can be genotoxic or carcinogenic or mutagenic and just not very good for human health. And then for dechlorination, it's basically just used to control residual chlorine. This is one, because chlorine can be very toxic to the aquatic ecosystem, so like fish and plant life in the ecosystem. And as well, we want to obviously try to reduce disinfectant byproducts, and we can use chlorination to do that because obviously the disinfectant byproducts are very toxic to human health. All right, so now into the modeling objectives. Basically, we've built a model in GPSX that we believe captures the main processes and effects of chlorination and dechlorination. So these are basically here the processes and kind of the outcomes that we think are important for a chemical disinfection model to be able to predict. So these are the basically prediction of the chlorine residual, the estimation of that disinfection byproduct formation potential. We want to be able to estimate the disinfection efficiency. We want to be able to approximate the chemical consumption, and we need the model to be able to predict changes in pH. So now I'm just going to spend a bit of time explaining how the model works and basically how the model can be used to do all the things that we have here on the slide. So the first one of these is predicting the chlorine residual. So there's 4 different sets of processes in the model for this. The instantaneous chlorine demand, the chlorine decay or inactivation due to detention time, the breakpoint chlorination reactions, and then the dechlorination reactions. So before I get into exactly how we predict a chlorine residual, I want to briefly just talk about what the actual chlorine residual is and just remind anyone who doesn't actually, or who needs a reminder on chlorine residual and free and combined chlorine. So for those of you who don't know, chlorine residual is basically just the concentration of chlorine in the stream leaving the chlorination basin. And you typically want it to be below or around 0.5 milligrams of chlorine per liter. And what free chlorine is that basically when chlorine is added to water, it rapidly hydrolyzes and forms hypochlorous acid and hypochlorite. So that's HOCl and OCl minus as seen on the slide there. And what combined chlorine is actually chloramine. So this is basically when chlorine reacts with ammonia in the water, it forms these combined chloramine chlorine. And it's also measured in milligrams of Cl2 per liter. And then as you can guess, total chlorine is just free chlorine and the combined chlorine added together, still measured in milligrams of chlorine per liter. All right, so back to these key components of the chlorine residual. I'm just going to mention them one more time. We have the chlorine demand, the chlorine decay, the breakpoint chlorination reactions, and the dechlorination reactions. And this table here just kind of shows the common wastewater constituents that can affect the chlorine residual because they react with chlorine or hypochlorous acid, to be more specific. And these items in the table here are going to show up as inputs in the 4 processes in our chlorine residual model. So these constituents are ammonia, organic nitrogen, BOD, COD, and TOC, inorganic compounds like iron and magnesium, nitrite, and sulfur dioxide, which is used for dechlorination. And only the first 2 have any disinfection benefit, the ammonia and organic nitrogen, because they actually produce chloramine, which can still be used for disinfection. But the other ones we would really like to minimize. Well, the next 3 we'd really like to minimize as they can react with chlorine, but don't actually help disinfection. They can actually produce disinfection byproducts, which are obviously bad for our health, as we've mentioned. And then obviously sulfur dioxide, we just use when we need to try to remove some of that chlorine to reduce the chlorine residual. Okay, so I'm going to get into the first process now affecting the chlorine residual. And this is the instantaneous demand calculation. So in GPSX, we use an empirical relation that uses the chlorine dosage, the UV254 absorbance, and the soluble total organic carbon to basically calculate the chlorine that is expected to immediately react with organics. So that is the instantaneous demand, and the inorganics in the wastewater. We calculate UV254 using a surrogate relationship with the soluble inert organic concentration. And basically, the way that this kind of model works is that any increase in any of these values here, so that would be the chlorine dosage, the UV254, or the total organic carbon, leads to a higher instantaneous demand. But there is some flexibility here. The user can toggle the instantaneous demand option on and off if they feel they don't need it in their specific layout or process. And the user can also calibrate the relationship by changing the empirical constants that you see here, these A1s through A4s on the slide. Okay, so the next process here that we're going to talk about that affects the residual chlorine is the chlorine decay. And the chlorine decay basically accounts for the chlorine that decays due to the detention time in the chlorination basin. It's represented by a kinetic model that basically relates the T10 detention time to the chlorine decay using a decay coefficient. So the definition of the T10 detention time, for those who don't know, is the time it takes for 10% of the volume of a certain unit, so in this case, the chlorination basin, to pass through that unit. So the time it takes for 10% of the volume of the chlorination basin to pass through the chlorination basin. So it's basically used as like a realistic or more conservative estimation of the retention time. And if you need to, you can determine it via some sort of tracer test at your specific facility. So for this one, the user can also calibrate it as well. They can obviously calibrate by just changing the decay constant, but you can also calibrate by changing a GPSX input parameter called the T10 to detention time ratio. So basically, this is a baffle factor, which is multiplied by the, I guess, the nominal hydraulic retention time of the chlorination basin and is used to calculate the T10 detention time. And so now, I guess, once we've calculated the chlorine decay and the instantaneous demand, we use that net available chlorine in the chlorine ammonia reactions and in the byproduct formation. which I'm going to be talking about now. So first, the chlorine ammonia or breakpoint chlorination reactions. So for those who need a brief review, what I have here on the slide is a breakpoint chlorination curve. So basically what breakpoint chlorination is when there's a continuous addition of chlorine to water containing ammonia, this phenomenon that is represented by the curve here is what results. So just to go through this figure briefly, over here we have the y-axis with the chlorine concentration. Then we have the x-axis over here with the chlorine to ammonia ratio. And then here we have the secondary y-axis with the ammonia concentration. So in this first zone here, this is where you first start dosing chlorine. In this zone, chloramines are formed up to a chlorine to ammonia ratio of about 5. So basically all the ammonia is reacting with the chlorine and making chloramines. In the second zone here, all the ammonia has reacted. And basically now the free chlorine that's being added is reacting with the chloramines instead to form nitrogen gas. And then here in this third zone, all the chloramines and all the ammonia is all reacted. So any free chlorine or any chlorine that you're adding to the system is just showing up now as a free chlorine residual. So that's basically the basic idea of breakpoint chlorination, trying to get to this free chlorine residual over here to disinfect the wastewater. So this is how breakpoint chlorination looks in GPSX. In the newest version of GPSX that we actually just released last week, version 8.1, we have actually added nitrite to the breakpoint chlorination reactions. And the reason we did this is because high nitrite concentrations in secondary effluent can be a common cause of unexpectedly high chlorine demand. And obviously we want to be able to capture that phenomena in the model. Making the model as robust as possible is always good. So I'll just go through this figure now as I went through the last one. So here, same axis here, we have the chlorine residual on the y-axis. On the x-axis, we now have the chlorine dosage. And then on the secondary y-axis, we have the ammonia and nitrite concentrations in milligrams of nitrogen per liter. And I should mention that in doing the analysis for this figure, we assumed that there's 1 milligram per liter of ammonia and 1 milligram per liter of nitrite coming into the chlorination basin. You can see they're both at 1 here, looking at this axis when the chlorine concentration is 0. So the first section here is when we're just dosing, we start dosing the chlorine, and the chlorine starts reacting with the ammonia and with the nitrite in the reactor. And the way we have it in GPSX is that the ammonia reaction actually occurs 30 times faster than the nitrite reaction when they're present at a 1-to-1 ratio. And we just found this commonly in the literature, so we included it in the model. So basically you can see here that the nitrite concentration is decreasing a lot slower because a lot more of the ammonia is reacting at this point and getting converted into chloramine. In the second section here, we have nitrite reacting uninhibited. So basically all of the ammonia has reacted at this point and turned into chloramine. And what we also found is that the nitrite with reaction with chlorine is about 100 times faster than the chloramine reaction with chlorine. So the way we set up the model was that the nitrite is then going to react before the chloramine reacts. And then finally, in the third section here, the chloramine is reacting with chlorine just as in the other graph. And this is producing nitrogen gas. And this only happens when all the ammonia and all the nitrite have reacted. And then finally, the fourth section here, we can see that any chlorine added after that just becomes free residual because everything else here has reacted. All right, so the last process that I'm going to talk about that affects the chlorine residual is dechlorination. So as I mentioned before, dechlorination is sometimes necessary to reduce the chlorine residual if you want to meet regulations. And this is another new addition that we added to the chemical disinfection model in GPSX 8.1. I also want to note that the dechlorination reactions actually occur after the disinfection reactions in the actual modeling sequence. And these disinfection reactions I haven't actually discussed yet. We're going to be discussing them later. But just because the dechlorination reactions do affect the chlorine residual that comes out of the chlorination basin, I'm going to be discussing them now just for continuity's sake. So getting into it here, you can see dechlorination is actually a fairly simple process. It's modeled using sulfur dioxide equivalents just because sulfur dioxide is the most common dechlorination chemical. So you can see when you add sulfur dioxide to water, it reacts with the water to make the sulfite. And then this sulfite is actually the thing that reacts with the available chlorine residual. So it can react with either the free chlorine residual and produce sulfate, chloride, and hydrogen ion, or it can react with chloramine, in which case it actually produces, instead of the hydrogen ion, it's producing an ammonia ion. And we actually capture this in the model as well. So if you are going to dechlorinate a chloramine residual, you will see ammonia produced in the GPSX model. All right, so now I'm just going to do a very quick summary of the steps taken by the model to determine residual chlorine, and also just remind you of the key factors that affect the residual at each step. So the first one is the instantaneous demand, and this is affected by the dissolved organics and inorganics. The second one is the chlorine decay, and this is affected by the detention time. The third one is breakpoint chlorination, and this is mainly affected by the ammonia and the nitrite concentrations entering the chlorination basin. And then the third one is dechlorination, and this is just majorly affected, obviously, by the dosage of the dechlorination chemical. And when this whole process is done, what we end up with here is a chlorine residual prediction that can end up being a free residual or a combined residual, basically just depending on the extent of the breakpoint chlorination reactions. All right, so now I'm going to move on to the next part of our modeling objectives, which is the disinfection byproduct estimation. So this includes two disinfectant byproducts that we're modeling in GPSX, the trihalomethanes and the haloacetic acids. So I'll start with the trihalomethanes, and the trihalomethane formation is calculated from the chlorine residual, and this calculation does take place after all the residual calculations that I just described are completed. And this is an important thing to note because that means that you can use dechlorination within the GPSX model to decrease the disinfectant byproduct formation, because these reactions won't be calculated until after the chlorine residual has been dechlorinated, if you so choose to use dechlorination. So this model is basically another empirical model similar to the decay model and the instantaneous demand model I showed. And it contains many of the terms that we've seen already from the other correlations, such as the UB254 term and the TOC term. But we also have some new terms here. This one is actually dependent on pH and bromine concentration. And bromine in this case is actually just a user input to the chlorination model. It's not a state variable calculated in GPSX. So the general behavior of this model is that basically any increase in any of these terms here, so the UB254, the chlorine residual, the bromine concentration, pH, any of those terms, if they increase, that's going to result in an increase in the trihalomethane concentration. But there's still that flexibility that I mentioned with the other ones where you can calibrate by changing all these parameters. They're all input options in GPSX should you want to calibrate the model at all. And the last thing I want to mention here is that we also calculate byproducts on the chloramines, but the formation of trihalomethanes is observed to be lower when the residual is a combined chloramine residual versus a free chlorine one. So we add a factor of 0.2 to reduce the byproduct formation in cases where there's a chloramine residual instead of a free chlorine residual. All right, so next I'm going to talk about the haloacetic acid byproduct formation. And like the trihalomethane ones, this calculation takes place after the residual calculations are completed. And again, you can use dechlorination to affect the byproduct formation in the same way you can with the trihalomethane concentrations. So this is also an empirical model, which just like before, contains many of the terms we've seen in the other correlations. So I'm not going to go into them too much. But also like before, the general behavior of the model is that increasing any of these terms, these input terms to the model, is going to cause an increase in the byproducts. Except for the bromide term, that actually causes a slight decrease in the byproduct formation if there's a high bromine concentration in the chlorination basin. And as before, the model can be calibrated by changing any of these empirical parameters. Okay, so now I'm going to move on to estimating the disinfection efficiency. So in terms of model calculations, as I mentioned before, the disinfection efficiency is actually calculated before we do the dechlorination calculations. So I have this, the residual chlorine calculation flow scheme I showed you before, and I just wanted to show where the disinfection efficiency calculation would fit on there. So it's basically just before we do the dechlorination, we are actually calculating the disinfection efficiency. And this is a good thing to note because basically, even if you are overdosing chlorine or something like that to ensure a very intense disinfection, and then doing a very heavy dechlorination, you're not going to lose any information in the model. That way, the model will capture that behavior well. So there are two disinfection reactions. There's the log inactivation of microorganisms and the coliform count that are both calculated in GPSX. So the log inactivation term is a mechanistic correlation that does consider kinetics. It uses that T10 detention time I mentioned before. And the coliform count is then simply calculated from that log inactivation term. You can see the figure I have here. It's just kind of to illustrate how this actually looks in GPSX. This is actually taken directly from a GPSX output. And it basically just illustrates that the log inactivation, as it increases in a pretty linear fashion, you can see that the coliform count is decreasing exponentially. And one more thing I should mention is that the initial coliform count here is a user input. So you're going to have to input that into the model, like into the actual disinfection object. It's not like a state variable that is carried along throughout your entire plant. Okay, I'm finally going to get to the last 2 points of our modeling objectives here, the chemical consumption and the chemical effect on pH. So I'm going to start with the chemical effect on pH. This is also a new aspect in the model in GPSX 8.1. We have previously had a pH estimation function for a while now, but now we've actually connected our disinfection model to it, so you can see how the different, I guess, disinfection and dechlorination processes affect the pH. So here at the top, I've listed all the chemicals that we have available for chlorination and dechlorination in GPSX. And the reason I've done this is because they actually, the choice of chemical has a non-negligible effect on the pH, and they actually can affect pH in very different ways. So the chemicals for chlorination are chlorine gas, sodium hypochlorite, and calcium hypochlorite. And the dechlorination chemicals are sulfur dioxide, sodium bisulfate, sodium metabisulfite, and sodium sulfite. All right, so moving your attention to the 2 graphs below, these are just 2 analyses that I did in GPSX using the pH estimation tool, just so that we can get a look at how the chemicals actually do affect the pH. So on this, I'll start with this graph here. This is the chlorination graph. So on this y-axis here, we have the effluent pH. On the x-axis, we have the chlorination chemical dosage. And then on the secondary y-axis here, we have the total chlorine residual. So the series on this graph, basically the NaOCl, the CaOCl2, and the Cl2 series all represent the pH, I guess, that happens when that certain amount of chlorine is dosed. And then this orange series just shows the residual, so how much chlorine, I guess, has been dosed, or the extent of the breakpoint chlorination reactions. You can see that this does resemble the breakpoint chlorination curve. So basically what you can see is that for the hypochlorites, there's actually a slight increase in pH overall when you are using them for disinfection, whereas with the chlorine gas, as we would expect, when using disinfectant with chlorine gas, there's a decrease in the pH. So you do have to keep those kind of things in consideration when you are selecting a chemical for chlorination. The second graph here is very similar to the chlorination graph, except for it's just showing the dechlorination chemicals. And again here, we can see, so this is the dechlorination chemical dosage, or I should say the dechlorination chemical residual, not dosage. And you can basically see here that as the all of the different dechlorination chemicals basically also have a different effect on pH. You can see the sodium sulfite actually increases the pH quite a lot, whereas the sulfur dioxide is actually decreasing the pH pretty significantly. All right, so finally, I'm just going to briefly discuss chemical consumption and how the model can be used to estimate it. So in this example here, I did not consider dechlorination just to simplify the analysis. All this is just done on chlorine consumption. And basically what I did was considered 3 different secondary effluent streams, all with slightly different characteristics. You could say that from effluent 1 here to effluent 3, the stream characteristics get a little worse in terms of water quality. And I wanted to evaluate how much chlorine would need to be added to each of these streams in a chlorination basin to achieve a 0.5 milligram chlorine per liter residual. So basically what you can see here is that even slight changes in the secondary effluent quality, so going from 0.3 milligrams of ammonia per liter to 0.36 or 0.27 milligrams of nitrite per liter to 0.41 can really change and have a significant effect on how much of the chlorine dose you're actually going to need in the model, as almost 4 milligrams more per liter, which can be quite a lot if you're flow pacing chlorine to a pretty high flow plant. So basically, this just highlights how important it is to be able to estimate chemical usage, and the chemical usage can obviously significantly affect your chemical cost budget. All right, so that's basically all I had for explaining the model. Now I'm just going to hop over to GPSX really quickly and just show you the chlorination model in a bit more detail and run a quick demo. So here we have the GPSX layout. This is actually the same layout that I showed on the first slide there with this chemical disinfection object. And first thing I want to show you is just the model selection here. So we have the chlorination model in the chemical disinfection object, which is the one I just basically taught you about. And then we also have this empiric model. And the empiric model is very bare bones. It's basically just disinfection, and it doesn't have all these additional aspects that we just talked about in the chlorination model. All right, so moving on to the input parameters here, I just want to kind of go through and show you where you can find all the things that I talked about. Here in the physical menu, we have the volume of the reactor, which is obviously an important consideration for chlorine decay and disinfection. And then we have this T10 to detention time and T50 to detention time ratios as well. So these are all important factors for the chlorine decay and the disinfection models that you're going to want to be able to change to fit your plant characteristics. Another input parameters I wanted to show you is the feed chemicals here. So you can select all the different chemicals I showed you here, any of these chlorination ones or any of these dechlorination ones here. You have the ability to specify chemical strength, the chemical density for both chlorination or dechlorination chemicals. And you can also choose if you want to use a constant dose of chemical or if you want to just have a constant chemical feed rate. And you can do this for both the chlorination and the dechlorination chemical. The next input menu I want to show you here is the TTHM model parameters. So this one actually contains a lot of the different model parameters from the empiric models that I showed you. You can see the instantaneous demand parameters here. So we have this option that I mentioned for if we want to turn off or on the instantaneous demand, we can easily do that. And we can also change all these coefficients to try to calibrate the instantaneous demand to our specific plant if we're noticing a difference in behavior. We also have this chlorine decay coefficient. And this is the decay coefficient that is used in the chlorine decay model. It can obviously also be calibrated here. And then there's all these empiric coefficients for the trihalomethane production. So this is the first of those disinfection byproducts I showed you. And then here we have all the different parameters for those 3 haloacetic acids. So yeah, you can see there's obviously a lot of different parameters and different options for trying to calibrate this chlorination model. So the next one I want to show you here is the stoichiometric coefficients. So these are more of like model stoichiometry and more derived from principles. So it's less likely you're going to be wanting to change one of these things, but you do have the option. So for example, we have the stoichiometric requirement of chlorine required for converting ammonia to chloramine. And then we have these other ones too for chlorine to required for chloramine to nitrogen gas. We also have the chlorine required for the nitrite oxidation, and then the sulfur dioxide required for dechlorination. So yeah, these are obviously they're derived from actual stoichiometry, so there's unlikely you're going to want to change them much, but you can obviously calibrate them a bit if that is what your plant calls for. Okay, the last one here I wanted to show you is the operating cost. So basically just all there is here is you can select your chemical purity and then also put in how much you're actually paying for your chemical. And this is obviously useful for cost estimation. And this I'm just showing here is the chlorination chemical cost setup, but we have the exact same thing here for the dechlorination chemical cost. Okay, so now I just wanted to do a bit of a sensitivity analysis just to kind of show you how GPSX does the sensitivity analysis and just show how it's kind of a nice way to just compare chlorination doses in a pretty quick way. So here I have set up the my chlorine dosage as my analyzed variable. So it's going to start at the 0 dose and go up to 15 in steps of 0.5. And we're going to see all these results here of what happens on this graph. I also want to mention that I have a dechlorination dosage of just 0.25, and I'm just going to hold that constant just so we can see what happens with dechlorination as we increase the chlorination dosage as well. I'm just going to start running this, and I'll keep talking over it as it goes. So another thing to mention is that this chemical disinfection unit is receiving secondary effluent. So there is a bit of ammonia, there is a bit of nitrite in there, and obviously some soluble organic carbon. And yeah, so these graphs that I have here, I've actually made by going into the menu here and clicking on output variables, and then we get all these different things that come up, and I can drag these over here and make all these graphs. So that's just an obviously nice feature of GPSX. I'm just going to go through them very quickly and just kind of explain what we're seeing in each graph in a very brief manner. So here in this chlorination graph, we have the orange total residual curve and the red chlorine dosage curve, and then the green free residual curve, which is obviously very hard to see as it's 0 while there's chloramine being produced, and then it exactly matches the total residual curve after the breakpoint. But the big thing to see here is just that GPSX does make a nice breakpoint chlorination curve when you're doing a sensitivity analysis on chlorine. Moving on to the nitrogen species here, you can see as I said before that the ammonia concentration is reducing. The ammonia is the black line here. It's reducing a lot faster than the nitrite concentration is, and that's just because of the way that the model is set up. And then when we get to the point where the ammonia concentration gets to its low point, then the nitrite can react uninhibited with the chlorine and be reduced very quickly. And the reason that we have this kind of discontinuity looking thing here is just because the dechlorination chemical is actually producing ammonia from the chloramine, and that's why this is high here. That's because there's a chloramine residual at this point, but then once the chloramine residual is gone, you do not see this anymore. As you can see over here, it goes down to its minimum limit. The next graph here is just the disinfection and pH graph. So this green line here is the most probable number of coliform, and the blue line is the inactivation of microorganisms. So obviously this is very similar to the graph I showed on the slides. You can see that obviously as the chlorination dose increases, this one is decreasing and this one is increasing as we would expect. And then this red line here is just the estimated pH, and it is slightly increasing as we dose the chlorine, as we would expect, because I'm dosing sodium hypochlorite in this example. So we do expect an increase in pH. This next graph is the dechlorination. So it has the dechlorination chemical dose as the black line here. It's constant, as I said, and then the dechlorination chemical residual. So basically, the reason we see these two kind of spikes is at the beginning here, there's obviously not a lot of chlorine being dosed. So that's why we see a residual amount of dechlorination chemical. And then over here, this is where the breakpoint occurs, and that's why we can see a residual amount of dechlorination chemical as well, because there's no chlorine for it to react with, so we obviously see some of it come out in the effluent. This graph here is the instantaneous demand in chlorine decay. As I said, and as can be easily seen now, increasing the chlorine dose raises these, but you can see that the chlorine decay, which is the blue line here, is actually much more sensitive to the chlorine dose than the instantaneous demand is, because the instantaneous demand is also has the like effluent, or not the effluent, but the secondary effluent quality built into it, whereas the chlorine decay just is more of a kinetic thing based on retention time. And then finally here we have the disinfection byproduct graph. And the big point with this graph is basically that you can see when in this section here, this is where we have a free chlorine residual versus this section here where we have that combined chloramine residual. We can see just how quickly the disinfection byproducts go up when we have free chlorine in the effluent. So it's just interesting to note that the chloramine obviously does have a much lower disinfection byproduct potential. Okay, so that is it for my demonstration. I'm just going to hop back into the slideshow now and give a brief summary. So today, basically, I discussed the chlorination and dechlorination model and a lot of the updates that we've put into it for GPSX 8.1. So this model is based on empirical and kinetic relationships, and it's able to predict the chlorine residual, the disinfection byproduct formation potential, the chemical consumption, the disinfection efficiency, and pH changes. And this model can be calibrated if you need to calibrate it to your disinfection byproduct formation or to your instantaneous demand, chlorine decay, or if you want to calibrate the nitrite and ammonia relationship. And there's a lot of applications for this model. A few of them include the ability to use it to optimize the disinfection process. It's obviously able to predict effluent chlorine and the toxic disinfection byproducts concentrations. You can use it to estimate your chemical cost, and you can use it as more of a general optimization if you're exploring cost-saving options for your whole plant. It can be one of the variables you're looking at. Basically, the chlorine dosage or the dechlorination dosage in this model can be one of the variables you look at in a more plant-wide cost optimization scenario. All right, here's just a couple useful references for further reading if you are at all interested in learning more about disinfection. And that is basically it for my presentation. I hope you enjoyed it. I hope you learned a lot from it. And I'm going to hand it back now to Spencer to provide some updates on GPSX.